Hello, my AP Chemers. We have been calculating pHs for strong acids and bases and then weak acids and bases. What if you had a mixture of acids or a mixture of bases? So let's look at this example here. We want to find the pH of a solution made by combining 10 milliliters of 0.02 molar hydrobromic acid and 10 milliliters of 0.035 molar iodic acid. So first thing you want to do is decide are these strong or weak? And so in this case, they are both strong. So if they're both strong, then the concentration of the acid is going to equal to the concentration of the H+, right? So this is the same thing as 0.02 molar H+, and this is the same thing as 0.035 molar H+, right? So if they're both strong, what you want to do is add up the amount of moles from both and divide by the total volume, and that's going to give you the total concentration of H+, and then you can find the pH. So I'm going to start by figuring out how many moles of HBr do I have, and therefore moles of H+. So 0.0100 liters times it is 0.020 molar, which is moles per liter. So liters cancel, and that gives me moles. That's from my HBr. And do the same thing for HI, so I have 0.0100 liters, and it's 0.035 moles per liter. My liters cancel, so I add up my moles and then I divide by my total volume, which is 0.0200 liters. When I do that, I get 0.0275 molar, so pH is negative log of that. And so my pH is equal to 1.561. Okay, so that's two strong acids. We do it this way because we know that the concentration of the H+ is going to be the concentration of your acid because it fully 100% dissociates. Now let's look at a mixture of weak acids. So I have a mixture of 1 molar HCN and then 5 molar HNO2. Now let's look at this. So there's HCN, it's a weak acid. Its Ka is 6.2 times 10 to the negative 10th. And HNO2 is also a weak acid. Its Ka is 4.0 times 10 to the negative 4th. Now you can since these are weak, you're going to need an ice chart, right? So you could do an ice chart for HCN, an ice chart for HNO2, figure out the moles of H+ that you end up with from here, figure out the moles of the H+ that you end up from here, add them together, divide by the total volume, similar to that last step here. Or if you look at the Ka values, you'll see that this is 10 to the negative 10th, this one is 10 to the negative 4th. This is huge. This is really, really big compared to this one, right? Or this is super small, it's negligible compared to this one. So what I would do in this case, I wouldn't worry about HCN at all because its Ka is so small, the H+'s from it are going to be very, 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 very small number compared to the H+'s that I get from HNO2. So I would ignore this one. I'd say this is negligible. And I would do just the HNO2. Now, if they were both similar, like one is 10 to the negative 4th and the other one is 10 to the negative 3rd or something like that, then yeah, I would do that. But I really doubt that they would do that to you on the AP exam because that's just too much calculations. But they could ask you this question just so that they can see that, oh yeah, you understand that this is negligible compared to this one. So really, all I would do is just this one. So I would do an ice chart here. Initially, this is 5.00 molar. 0 and 0, minus x plus x plus x, 5 minus x, x and x. Then you'd say Ka is concentration of H+ times the concentration of NO2 minus over the concentration of HNO2. My Ka is 4.0 times 10 to the negative 4th, x times x over 5 minus x. And x ends up being the H plus concentration is 0.00 445. So pH is negative log of that, which ends up being 1.351. The other scenario that they could give you is they could give you a strong one, like HBr, and a weak one, like HNO2, and ask you, what is the pH. In that case, again, you check. If the Ka is super small, then you just do the strong one and that's it, which is more than likely if they give you a strong and a weak. If the weak one had a still pretty high Ka, then you can do an ice chart for it, find the moles, and then find the moles of the other one and add them. But more than likely, if they give you a strong and a weak, you just do the strong, ignore the weak, because it's going to be negligible compared to the strong one. Our next topic is polyprotic acids. We had talked about polyprotic like diprotic or triprotic, meaning that it can give off more than one proton. So for example, sulfuric acid is diprotic. It can give off an H plus and HSO4 minus, but then HSO4 minus is a weak acid and it can give off partially some H pluses and SO4 2 minuses. Whenever you have a polyprotic acid, the second and third and successive ionizations are way, way less than the previous one. So, for example, with H2SO4, the first ionization is 100%, right? All of it ionizes. But then HSO4 minus only partially ionizes to the extent of 1.2 times 10 to the negative second as your Ka. Let's look at some more. So look at this one, for example, ascorbic acid. Its first Ka is to the negative fifth. Its second Ka is to the negative 12th. Way, way smaller than the first one. Citric has 3 protons. First one's 10 to the negative 4th. Second one's 10 to the negative 5th, so a little bit smaller. Next one's 10 to the negative 7th. So you can see that you get less and less and less ionization as you go. So when you have a polyprotic acid, the first proton is always the strongest, meaning the highest dissociation percentage, followed by the second one, followed by the third one, and so on. So they used to, in the past, ask you, hey, if I have H2SO4 or citric acid or something like that, any polyprotic acid, what is the concentrations of the different ions, or what is the pH or something like that? And you'd have to do 2 or 3 ice charts to get to that. That is out of the AP exam. You will not be asked to do computations with that. However, you do need to realize that the extent of dissociation decreases from the first proton to the second to the third, and be able to apply them. So let's look at this question. It says H2SO3 is diprotic. Which ion has the lowest concentration at equilibrium? So you're going to say, well, H2SO3 can partially ionize to form H plus and HSO3 minus. And then HSO3 minus can also partially ionize to form H plus and SO3 2 minus. So what you need to apply here is the idea that the percentage of this ionization is much higher than the percentage of this ionization. So let's say this ionization is 50%. So 50% of this turns into H plus and HSO3 minus. Well, then this one might be like 10%. So only 10% of this would turn into H plus and SO3 2 minus. So then which ion would have the smallest concentration? Well, it's going to be this one right here. Because in the example we just gave, if only 50% of it turned into HSO3 minus, well, only 10% of the 50% had turned into SO3 2 minus. So this is going to have the lowest concentration out of all your ions.